The objective of this case study is aimed at production of ethanol by utilizing spent biomass generated from seaweed processing industry using Becker's yeast and its potential of converting galactose and alginate monomers to bioethanol through fermentation. Next, key methodologies. Number 1, pretreatment of spent biomass using H2SO4. Firstly, mild acid treatment was optimized for hydrolysis of polysaccharide from spent biomass. Next, 10 ml of 0.1%, 0.5%, and 1% of H2SO4 was used to hydrolyze 0.2 gram of spent biomass and autoclave at 121 degrees Celsius for 50 minutes. Next, the hydrolyzed spent biomass were filtered using muslin cloth after cooling to room temperature. Next, the filtrate was centrifuged at 10,000 rpm, 20 minutes to remove insoluble substances present in hydrolysates. Then, pH of filtrate was 1.2 until 1.5 and adjusted to 5.3 using 1 m NaOH for fermentation. The hydrolysates were subjected to FT-Raman analysis to confirm presence of sugars and converted from other pretreatment. The quality of hydrolysate was assessed using FT-Raman spectra. This also can optimize the method of hydrolysis. Then, hydrolysis of different quantities of spent seaweed biomass with standard amount of acid concentration was carried out to optimize concentration of biomass to extract maximum amount of sugar from hydrolysates. Then, different quantities of brown seaweed biomass such as 2, 4, 6, 8, and 10 was used in 50 ml of 1% H2SO4 and autoclave at 121 degrees Celsius at 50 minutes. Next, fermentation process. First, Becker's yeast was used for saccharification. The yeast pellet was revived in yeast extract peptone dextrose, which is YDP, broth, high media, and subsequently subcultured for further use. The colonies were maintained on slants of YPD agar. Supplementary nutrients in G per L, urea, 1, and A2, HPO4, 0.5 KH2PO4, 2.5 MgSO4, 1, and H42SO4, 1 FeSO4, 0.001 were added to hydrolysates before inoculation of 10% V per V of yeast cell. The spent biomass concentration was maintained at 5.6 gram in 7 ml of acid. 100 ml glass vials containing 7 ml of sterile hydrolysate was inoculated with 7 ml of yeast and incubated at 30 until 34 degrees Celsius under shaking condition at 50 rpm. Vials were sealed with rubber corks and crimps. Next, YDP broth and D-galactose, which is SRL, concentration 20 gram per liter, were used as standards for fermentation to compare the production of ethanol with seaweed spent. Lastly, the temperature was maintained at 30 until 34 degrees Celsius under shaking, which is 50 rpm, for incubation of 5 days.
In the major findings of our chosen research paper. First of all, the paper found out that the total sugar content present in the red seaweed spent biomass was more than that of brown seaweed spent biomass. This could be due to brown seaweed was obtained after pycocolloids extraction, while red seaweed was obtained after pycobd proteins extraction. Next, it was found out that 8% weight over volume ratio of substrate was the most suitable for acid hydrolysis. Among the different concentrations of hydrogen sulfate used for spent biomass hydrolysis, low biomass weight and volume ratio show the maximum amount of reducing sugar yield. Last but not least, the ethanol yield from red seaweed biomass was higher than that of brown seaweed biomass because red seaweed contain more simple sugars.
So now let's continue with relevant discussion. First, the fermentation and ethanol yield. The ethanol yield from the red seaweed spent biomass was observed to be higher than brown seaweed spent biomass. So actually, before fermentation, they extracted the psychobilly because psychobilly pigment in red seaweed can interfere with fermentation process. By removing this pigment, more biomass can utilize for ethanol production, leading to a higher ethanol yield. While in brown seaweed spent biomass case, psychocolloid were extracted before fermentation, and this extraction may remove certain components that could contribute to higher ethanol production. That's why ethanol yield from brown seaweed was lower compared to the red seaweed. Then we move to phenol and protein content. Phenol can act as inhibitor to yeast growth and fermentation efficiency. So protein provide information about the composition of the biomass, and protein also serve as a nutrition source for yeast during fermentation and impact the nutritional value of the biomass. For comparison with other study, different study may focus on utilizing various species of macroalgae, so various pretreatment method needed, and then different conservation technology were used, such as anaerobic digestion for biogas production. And lastly, for practical application and implication, converting waste materials into biofuels promote waste valorization. It support commercial biofuel production and renewable energy sector, encourage sustainable energy generations, and advance the bioenergy development. That's all.
In conclusion, the chosen paper clarified the potential of spent biomass from industrial seaweed processing to be a valuable source of bioethanol production, with the red seaweed biomass being a more promising source than brown seaweed biomass. The paper also pointed out mild acid treatment, which is 1% of hydrogen sulfate, was effective in hydrolyzing complex sugars from spent biomass, and the resulting hydrolysates were suitable substrate for fermentation by Becker's yeast.